Today we're going to talk about inverses of a function. And this is a great section because it really pulls together everything we've learned the whole semester. So the inverse of a function simply is, well, what does inverse mean? Kind of like opposite, right? And so the inverse of a function switches the x and the y. The inverse of the function switches the x and the y. So if I was going to have an inverse of this set of ordered pairs, every ordered pair would just switch the x and the y, right? Something like that. So the original function had a domain of 3, 4, and 9, right? And then it had a range of 5, 6, and 10. And then when I switch it, the new inverse has a domain of 5, 6, and 10, and then has a range of 3, 4, and 9. So the domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. So same thing with the mapping. So in the original mapping here, the domain is 1, 2, and 3, and the range is 4. And if I were to do the inverse, the domain would be 4, and the range would be 1, 2, and 3. Like that. Here I'm going to actually do a little t-chart of those ordered pairs. So it looks like 0, 0, negative 1, 1, negative 2, 2, negative 3, 3. So the original domain 0, negative 1, negative 2, negative 3. And by the way, you don't have to have those brackets, right? And the range would be 0, 1, 2, and 3. If you do the inverse is going to switch the x and the y. So I would take those ordered pairs, and now in the inverse, it's going to be, well, 0, 0, right? 1, negative 1, 2, negative 2, 3, negative 3, like that. And again, it's just those dots, not connecting them. So this domain here is 0, 1, 2, and 3, and 0, negative 1, negative 2, and negative 3. When the graph is connected, like y equals 2, okay, so we know that this graph has a domain of all real numbers and a range of 2. And we could even make a little xy chart like 1, 2, 3, and all the y's are 2. If we do the inverse xy would have all the x's of 2's, and the y's can be like whatever, all real numbers. And so the inverse of a horizontal line is a vertical line. So now we're going to talk about any equation or any function, how we're going to solve for the inverse. So the first thing we're going to do is we're going to replace the f of x with y, which we're more comfortable with anyway, right? We're always more comfortable with y. Then our main step for inverse is going to be switch the x and the y. Switch the x and the y. And then we're going to solve for the new y. Solve for the new y. And then we're going to replace the new y with f inverse of x. Like that. So here with this linear function, right, can you tell it's linear? Y equals 2x minus 4. I'm going to graph that. Y equals 2x minus 4, up 2 over 1, up 2 over 1, up 2 over 1. I'm going to do that several times. And do you agree that the domain and the range of any linear function, as long as it's not vertical or horizontal, is all real numbers? To find the inverse, I'm going to switch the x and the y, so x equals 2y minus 4. Solve for the new y, x plus 4 equals 2y. And I'm going to rewrite that y equals 1/2 x plus 2. So that I can really tell that the inverse here is also a linear function. And if I graph that, up 1 over 2, up 1 over 2. So the inverse of a line is a line. Domain and range is all real numbers. And then just fun fact, what's the ordered pair of the point where those two lines meet? The function and its inverse. 4, 4. Why does that make sense? What happens when I switch 4, 4? It's also 4, 4, right? So the inverse of a line is a line. The next one's quadratic, right? This is a parabola that's moved right 3. Domain is all real numbers. Range is greater than or equal to 0. If I want to find the equation of the inverse, I'm going to replace the f of x with y. I'm going to switch the x and the y and solve for the new y. So when I square root both sides, plus or minus root x equals y minus 3. And if I add 3 to both sides, that is the equation of the inverse function. So f inverse of x plus or minus root x plus 3. If I graph that, I should have done a different color. If I graph that up 3, and then here's plus or minus root x. So the domain there is greater than or equal to 0, and the range is all real numbers. So the inverse of a quadratic is a radical. And I'm going to go back and fill this in. The inverse of a linear is a linear. So lines are inverses to lines, quadratics are inverses to radicals. If I go to the next page, I've got my rational, right? This is rational. And this one's a little bit different, right? This is not our easiest graph because we've got these asymptotes, right? So in the original function, remember that x is not allowed to be 0 and the range is not allowed to be 0. And then we get this like swooshing thing, right? If I want to find the inverse, I'm going to make it y equals 3 over x, switch the x and the y, solve for the new y, and what happens? What? The rational is its own inverse. Now, this only happens when you have kind of a simple rational equation. If I had anything adding or subtracting, it would be a rational. It wouldn't be the exact same one. This one happens to be the exact same one. And I just did that because it's like an easy one to start off with rational. So not every rational is its own inverse, but every rational is an inverse of a rational. Next one, y equals plus or minus root x. This is radical. The domain is greater than or equal to 0. The range is all real numbers. If I want to find the inverse, y equals plus or minus root x, switch the x and the y, and then what am I going to do to both sides? Square both sides. Y equals f squared. The inverse is quadratic. The inverse of a radical is quadratic, which makes sense because the inverse of a quadratic was radical. All real numbers, y is greater than or equal to 0. Almost done. Last two. What kind of graph is number 5, or what kind of function? Exponential, right? Exponential goes to the point 0, 1 and swooshes up. So our domain is all real numbers, range just greater than 0. If you want to do the inverse, replace f of x with y, switch the x and the y. Now to solve for the new y, I'm going to just rewrite this as a log. The log base 2 of x equals y. We've done this before. The inverse of an exponential is a log, right? And it comes down like this, with x is greater than or 0, and then all real numbers. So this is just from our last chapter, right? So similarly, a log, and this is understood to be log base 10, so it's going to be a little steeper. Your graphs don't have to be perfect. X is greater than 0, all real numbers. If I want to do the inverse, y equals log understood to be base 10 of x. So x equals log base 10 of y when I switch the x and the y. And if I log loop it, y equals 10 to the x. Or the inverse here is 10 to the x, which, this is much steeper than what I can really represent on this graph. All real numbers, y is greater than 0. So then, kind of as a grand finale, what is the relationship? I'm going to tell you and then I'm going to show you. The graph and its inverse are a reflection over the line y equals x. So in all these graphs, I can go back and draw in a line of symmetry. Remember that from geometry? A a line of symmetry that's going to follow ordered pairs like 4, 4, 3, 3, 2, 2, 1, 1, 0, 0. If I were to take my original line and reflect it over the line y equals x, whoops, I would get the inverse. So that's like kind of an aha moment. And then just to wrap it up, the inverse of linear is linear. The inverse of quadratic is radical. The inverse of radical, I'll go down there, is quadratic. The inverse of rational is rational, not always the exact same, but definitely another rational. The inverse of exponential is log, and the inverse of log is exponential. So there you have it. Everything we learned this semester tied into one section on inverse functions.